Hello everyone, in this video, I'm going to present Share More and Talk Less, Optimal Distributed Testing and Randomness and Communication Constraints. I'm Ziteng Sun from Cornell, and this is a joint work with Jaradev, Clement, Yanjun, and Himanshu. A huge amount of data are generated from different devices every day, including laptops, smartphones, and even cars. Doing inference tasks on these data can be of interest to many applications. One of the questions we want to ask is, does the data satisfy a postulated hypothesis or property? However, in the distributed setting, there can be many constraints we will incur. The mobile devices can have low battery or unstable connection. There can be privacy issues with the data, or the data will incur noise during transmission. In consequence, the central referee can only observe constrained observations. In this talk, we are going to consider how to handle some of the constraints for the task of identity testing. The task is defined as the following. So you have a discrete set of size k, and there is a known distribution q over the domain, and you observe n independent samples from an unknown distribution p over the same domain. The question is whether p equals to q or not. The goal is to come up with a test which satisfies the following. With probability at least 1 minus delta, the test should output 1 if they are the same distribution, and it should output 0 if they are far away in TV distance. In this talk, we consider the error probability to be 1/3, and there are many common techniques to boost the probability to arbitrary delta, and such as median trick or reputations. But in the randomness constraint setting considered in this talk, we are going to present a deterministic amplification technique to boost the probability without using extra randomness. The sample complexity of this task is defined as the smallest number of samples needed for such a test to exist. In the centralized setting, without any constraints, the sample complexity is known to be root k over epsilon squared. What will happen in the constraint setting? Let's first define the constraints first. In this talk, we consider simultaneous message passing protocols, where each user simultaneously passes their sample through channels and sends the messages to the central referee. The referee has to make a decision based on the outputs of the channel. Each of the channel WI has to be a constraint set script W, which describes the local information constraints. What kind of local information constraints are we considering? The first is communication. Only L bits is allowed from each user. In other words, the output alphabet of each user is at most 2 to the L. And the second is privacy. WIs has to satisfy row local differential privacy, which requires that for any distinct pair of inputs, x and x prime, and any y in the output alphabet, the probability ratio between outputting y conditioned on x and outputting y conditioned on x prime is at most e to the row. You can see the smaller row is, the closer the output distributions are, and the more privacy you have. And there can be other constraints like restricted measurements, for example, linear measurements or noise measurements. There are many related works in this area, including identity testing, communication limited inference, and LDP constraint inference, and there are many more. In this talk, we also consider another aspect of the protocols, which is how are the channels selected. The first kind of protocol is called private coin protocols. In this case, each user has his or her own dice, and they can throw the dice arbitrary number of times to generate independent random seeds at each user. And then each channel is selected based on the realization of the user's own random seed. You can see that if the set script W is convex, this is equivalent to, at each user, they select a deterministic channel bar of WI, which is equal to the expected channel he will select over the randomness of the random seed. Another type of protocol is called public coin protocols. In this case, there is a shared dice observed by all the users. You can throw the dice arbitrary number of times to generate a shared random seeds available to all the users and the referee. And each of the channel is selected based on the realization of the same random seed. You can see that you can always simulate a private coin protocol using a public coin protocol, but are they equally powerful? In one of the previous works by Acharya, Kano, and Tyagi, They show that there is actually a gap between public calling protocols and private calling protocols for the task of identity testing. You can see that for let's focus on the communication constraint case. And for public calling protocols, the sample complexity is increased by a factor of root k over 2 to the L, when L is less than log k. And for private calling protocols, on the other hand, the sample complexity is increased by a factor of k over 2 to the L. You can see there is actually a gap. In this work, we asked, what if we only have limited shared randomness, which means we can only throw the dice S times, which corresponds to other S bits of shared randomness. In this work, we established the optimal sample complexity under S bits of shared randomness as the following. You can see that the sample complexity is increased by a factor of root k over 2 to the S over 2 multiplied by 2 to the L in the limited shared randomness setting. And when S is roughly 0, this corresponds to the sample complexity for private calling protocols. And when S is roughly of order log k, this corresponds to the sample complexity for public calling protocols. And another remark we want to make here is that if you look at this bound, this tells you that roughly 1 bit of shared randomness is worth half a bit of communication in this case. How can we achieve this? From these bounds, you can see that the larger domain we have, the more samples we need to achieve the same performance. So the high-level idea of our approach is use shared randomness to embed the problem into a smaller domain, and hopefully this can reduce the sample complexity of the problem. More specifically, we introduce the following domain compression primitive, which gives a set of mappings that map an element from the domain K into a new domain of size L. It satisfies the following property. If we select a random mapping uniformly from the set, with probability 1 minus delta, for any distributions over the original domain P and Q, the distributions introduced by the mapping, P of F and QF, preserves the distance between P and Q up to a factor of theta. We want this to hold for small l and large theta, and it should succeed with high probability, so we want small delta, and we want this to hold for a suitable notion of the distance, d. You can see that if we have this primitive, we can reduce the problem into a small domain in the following way. The players use the S bit of shared randomness to apply the same mapping F in the set. Because the set is of size 2 to the S, so we can use S bits of shared randomness to select a uniform mapping. And since the distance is preserved, we can now use the private randomness scheme over the smaller domain to solve the problem. Before going into the details, let's look at how private calling schemes and public calling schemes works. From now on, we will focus on the case with communication constraints, and each user can only send 1 bit. Because each user can only send 1 bit, they cannot send their original samples. What we will do is we divide the domain into king singletons, and we also divide the users into k subgroups, each with size n over k. Within each group, the user sends whether their sample lies in the corresponding singleton or not. You can show that up to constant factors, with this procedure, we can reduce the problem to a uniformity testing problem with number of users n prime equal to n divided by k. Okay, and if we plug in this number into the original bound in the centralized setting, we can get this bound of root k over epsilon square times k, which is tight for private calling schemes. For public calling schemes, we divide the domain into 2 subsets, each with size k over 2. And the original distribution is mapped to a binary distribution over the 2 subsets. Previous works by Achaya, Kanu, and Tiarki shows that if this subset is chosen uniformly at random from all subsets with size k over 2 using public randomness, then the total variation distance is preserved up to a factor of 1 over square root k with constant probability. Moreover, we can see that the uniform distribution is also mapped to the uniform distribution. Now, the problem is reduced to a uniformity testing problem with k prime equals to 2 and epsilon prime equals to roughly epsilon over root k. Using the previous bounds in the centralized setting, we can get the following bound of square root k over epsilon squared multiplied by square root k. You can also show that this is tight for public coin schemes. But now we are in a randomness limited setting, and selecting a random subset is not randomness efficient. And specifically, you need order k bits of shared randomness to select a truly uniform random subset of size k over 2. So in this work, we prove this derandomization lemma, which shows that instead of selecting a uniform random subset of size k over 2, there exists m subsets where m is of order k, such that if we select a uniform random set from these sets, the same performance holds. A few remarks. The first is that these subsets, these m subsets, are chosen before p and q, so this holds for all p and q's. The second, m is roughly order log k, is also necessary, because when m is smaller than k, by solving a linear system, you can always find two distributions that are mapped to the same distribution after the mapping. What this shows is that order log k bits would suffice to achieve the public coin performance. What if we have less than that? In this work, we also propose the following domain compression theorem, which shows that for any constant theta, we can find a set of mappings of size order 1 over theta squared. Each of them maps the original domain of size k to a new domain of size L, which is equal to theta squared k. When we select a uniform random mapping from the set, with probability at least 1 minus delta 0, the total variation distance between the induced distributions are preserved up to a factor of theta. Now we have this theorem, how do we select these parameters? First, since we have s bits of shared randomness, and the set is of size order 1 over theta squared, so we can select theta to be 1 over square root 2 to the s, so that we can use the s bits of shared randomness to select a random mapping. Now, the new domain size is of order theta squared k, which is k over 2 to the s, and the new distance parameter epsilon prime is now roughly epsilon over square root 2 to the s. A few remarks. So each of these mappings is an almost equal partition of the domain, and similar results also hold for L2 if you prefer that metric. With this domain compression primitive, we can reduce the uniformity testing problem over the original domain to a new problem where the domain size k prime is k over 2 to the s, and the new parameter epsilon prime is epsilon over square root 2 to the s, with s bits of shared randomness. Now recall the 1-bit protocol. We can divide the users into n divided by k over 2 to the s groups, and each of the group is in charge of one of the singletons in the new domain. And now we can reduce the problem to the centralized problem with the new number of users n prime equals to n divided by k over 2 to the s. Now if we plug in these new parameters, we get that the sample complexity of the original problem is roughly k over epsilon squared multiplied by square root k multiplied by square root k over 2 to the s. The s is less than log k. There is also one small catch here, which is that the original domain compression theorem succeeds with a relatively small constant probability. If we use the boosting using repetition technique commonly used in the centralized setting, it will require more shared randomness. Here we propose a solution which is called deterministic amplification, which can boost the probability to a larger constant without using extra shared randomness. Please read our full paper for the details. This concludes the upper bound part. Now we provide our lower bound idea briefly. We study the role of a limited amount of shared randomness in establishing min-max lower bounds. Consider a game between the learner and the adversary, where the learner chooses a set of communication channels, and the adversary chooses a prior on the underlying distribution to confuse the learner. Without shared randomness, the channel Wn has to be a product channel, since each Wi is selected independently. But with shared randomness, we can coordinate the selection of channels among the users. And now W to the n can be a mixture of product channels. With this in mind, we introduce the following semi-min-max framework. Suppose I is a suitable notion of information that the learner wants to maximize by selecting W to the n, and the adversary wants to minimize it by selecting pi. The semi-max-min framework is defined as the following. The learner first chooses a set of product channels script W, and then the adversary chooses a prior pi to confuse the learner. After that, the shared randomness is used to select a random product channel from the set, and the information obtained by the learner is the expected information over the randomness. When S equals to 0, this recovers the max-min information for private randomness, and when S equals to infinity, this is upper bounded by the min-max information for public randomness. This framework can be of independent interest in the randomness limited setting. To conclude, we propose a randomness optimal domain compression scheme, which can embed statistical problems into a smaller domain while preserving their distance. Using this primitive, we obtain tight trade-offs for randomness limited identity testing. Please read our full paper for details if you are interested. Thank you.